In this series of videos, just like in chapter 4, I'm going to take you through another GoLang implementation of a hash function. This time it's going to be RIPEMD 160 instead of SHA-256. What was interesting about RIPEMD 160 is it follows the same Merkle-Damgard structure as SHA-256. So we have our input and pre-processing, our compression, and then our final value construction and output. So this video is going to be about input and pre-processing, and then the next video will be about compression, and then the final video will be about final value construction and output. So let's get started. So before jumping into the code in this series of videos, I just want to bring up the paper that Hans Darberton, Antoon Bosselaris, and Bart Pernille wrote, RIPEMD 160, a strengthened version of RIPEMD, and this is basically the specification for RIPEMD 160. And so I'm just going to jump down to the bottom here where the pseudocode is given. And so this is the pseudocode for RIPEMD 160. A couple of things to point out here for this pre-processing part. So it's an iterative hash function that operates on 32-bit words, just like SHA-256. And then it takes a 5-word chaining variable rather than 8 like SHA-256 did, and a 16-word message block that would be 512 bits just like SHA-256. And the reason why is because they both took that from MD4, and MD4, MD5 proved that 512-bit message block with that padding amount was secure. And so instead of trying to reinvent that, they just both hash functions just use that in their own hash functions. And that's another thing about the Merkle-Damgard family of hash functions. So you can just keep that input part the same, and then really all that's changing is the compression function and then the output length as well. And so you'll see there are a few differences here. We have different logical functions being used, but even though there are some differences, it's still kind of the same process because they are both Merkle-Damgard functions between SHA-256 and RIPEMD 160. So we have constant values here. They're also given just like SHA-256. And then we have, what's a little bit different here is we have our rounds here. So we're doing 5 rounds. So we have our 16-word message schedule that we get from our message block. And then we're doing 80 rounds in total. Basically, that gets split into 2 different sets of working variables, and they're run in parallel, more or less. We'll get further into the details of the compression function when we get to it, but basically what this is doing, it's denoting which words from the schedule are being used in that part of the compression function. So then the other part of that is there's also a rotate left. That's part of the compression function, and this just denotes which word is being rotated, or by how much that rotate left is occurring, how many times that's happening. And then you have your initial values, just like SHA-256, and here is the actual pseudocode for the compression function. And then another nice little include in here, there's a nice diagram there of it, but also some test values are given. And so you can test against these to see if the hash function is working properly. So now just jumping into the code, if we jump into our main file here, the main function is doing basically the same thing that the SHA-256 main function was doing. We have 2 ways of feeding data into this hash function. Either we can feed that data in directly as an attribute or as a parameter, or we can pipe it in using the command line. And then we have our get hash function here. So it is basically the same thing because they're both SHA-256 and RIPEMD 160 are Merkle-Damgard functions, and they're both using that 512-bit message block. And so we have our message here, and we have our byte inputs, and we'll use the same ABC input example like we did for SHA-256. And so what we're doing here, we're building our message block, and we can just jump to that definition, build message block. So very similar to SHA-256. We are first creating blank byte array here, and then we're appending our message in bytes, and then we're adding our 0 padding bits, which just like SHA-256, it is 448 bits congruent to 512 bits. We can just jump up here and have a look at that again. So that's our how much padding function. and we take our message length, and then we modulus that by 64, and if it's less than 56, we know that it's going to be one block, and so we just do this, 56 minus message length mod 64. Otherwise, if it's going to be more than that, then we want to make sure that we have enough padding to get the right block size, because it's congruent. So we go 64 plus 56 minus message length modulus 64. And then we're adding our separator bit, so this adds that 1 to the leftmost bit in the byte. And then we are appending all of that to our message block. And finally, we're adding our message length. And so there is one key difference here. And the key difference is RIPEMD 160 continues to use little endian values like MD4 and MD5 do. And so in SHA-256, everything was in big endian. However, in RIPEMD 160, it uses some little endian values. So here's an example of that. So the message length, so those 24 bits at the end of our message block, are actually in little endian format instead of big endian format. And so we can run a Go test verbose on this pre-processing test, and we'll do message block test file. And so if we have a look at this here, we're just following this process. So we have our blank or our empty byte array, then we're adding, this is our ABC output, and then what we're doing is we're putting our ABC output into our empty byte array, and then we're adding our separator bit here, then we're adding the necessary padding to get 448 bits congruent to 512, and then we are adding our length. And this is where it's a little bit different from SHA-256. So you'll see at the end here, these last 64 bits, these last 8 bytes, are in little endian. So in SHA-256, this 24 value here was in this spot. Whereas now in RIPEMD 160, because this is in little endian, this length is in little endian, it's in this spot here. So those bytes have been reversed. So once we have our message block, if we jump back to our main function here, the next step is to get our message schedule. So we can do a jump to definition there. And this is a lot less complicated than SHA-256 was, because it's not a 64-word schedule, it's a 16-word schedule. So all we're doing, just like SHA-256, is we're taking our message block and we're just putting that into a message schedule. And so fairly straightforward. All we're doing is running a loop here, and we're taking each 32 bits of this message block, and we are putting this in little endian. So it's a word, it's a 32-bit word, but it's also being put in little endian here. So that's kind of another key difference between RIPEMD and SHA-256. Not only is that message length in little endian, but also all of the words in the message schedule are also in little endian. And so we're just basically, this variable here is corresponding to our message block, and then we're just taking the 32-bit values, which is 4 bytes, 1, 2, 3, 4, and we're plugging those into an array of those unsigned 32-bit integers, and we're doing that in little endian. And that pretty much covers off this first part, the input and the pre-processing part. If we jump back to our main function here, our main file, the next step is compression, and we'll cover that in the next video.